Alright, so just wanted to go through. The first one was, it's not really a doubt, but it's more like a observation which I want to talk about out loud, because a lot of students go through this and very few ask this question out loud. As a student, I have also had this question. So the question is, I find it difficult or a bit stressful to enjoy learning a course which I innately like after making mistakes or not performing well in exams. Any suggestions on outlooks so that I don't doubt myself or question my capability? So does this sound familiar? To whom does it not sound familiar? Anyone wants to raise their hand? Okay, so I mean, it's familiar to everyone, including me, right? As a student, I've also had some courses where my head is just above the water. Okay, and so what is it that I can suggest is, there's no short-term answer for it, because if I tell you something, it will not really make sense. But I can tell you, with the benefit of some time having passed, after, let us say, 1, 2 or 3 years have passed from this course, you will forget the bad experience of mistakes and poor marks. That forgets. But if you found the course interesting, you remember that part. You remember being, feeling curious in class, finding the content interesting, and that is the part that stays with you. And I can tell you this by personal experience. So many courses during my PhD I found very difficult, because I tried to switch out of electrical engineering into physics. So I tried to cover up all the physics courses, taking the courses with other students who had a bachelor's in physics. So it was very hard, right? So every problem, and there we used to have every week one problem set for every course. So it was very hard. So there were some courses where I barely made it through. But after having graduated, or even a few years after that, I felt, okay, I'm so glad I did not drop these courses. One is that you remember the good stuff. The bad stuff has a shorter time constant. The second thing is that, let us say you're interested in making a career in a technical career. And later on, like courses like optimization, probability, linear algebra, they're very basic courses. No matter what you do, the next 30 years, you're going to use these tools. Now, what happens if you drop a course as important as, let us say, this or any other basic courses? The next time you come across the next new fad, today it's machine learning, tomorrow it's, I don't know what, machine unlearning or something like that. Every time you go to learn that course, you will face one big mental block. Oh, I couldn't understand optimization. There is no chance I'm going to understand this new area. And it's just a mental block. So you are making it harder for yourself in the future. The other thing is that, I mean, this is a practice for real life. In real life, when you step into the real world of either a job or whatever else, you are going to have multiple deadlines that you cannot meet, multiple expectations of you that you cannot meet. This is relatively much simpler. So it's more like training ground. It's difficult, okay, it's difficult for everyone. Try to make it work. And I can assure you, you will not regret it later. It's easiest, so every time there's a difficult lecture, let us say, or a difficult quiz, I see the drop requests that come in my workflow. Okay, and what is it saying? That the first sign of difficulty, you say, let's drop. But that's bad practice in general for life, right? It's never going to, this is the easiest you will get it. It's only going to get tougher. So may as well, get on with it. Anyone wants to share anything related to this? Anything that helps them to not drop a course or not feel lousy about themselves? Anyone? That you tried and it worked and you felt, okay, this is useful. Someone else may also learn from it. Yeah. You're taking the course for the second time. Okay. Okay. And so what made it different for you this time? So let me do it this time. Okay. So if your drop request comes, I'm going to reject it, right? All right. Good. That's a good spirit. Anybody else? Problems. Okay. Help. Well, from now you're going to have a steady stream of tutorial questions and so on. So no worries on that account. Okay, let's continue. Let's see. So there were a couple of doubt sheets with a unusual naming convention. So it says in today's class I got an introduction on conjugate gradient descent. This method is not conjugate gradient descent. This is conjugate gradient method. There's no descent in the name of the word. If you use the word descent, you're going to confuse yourself a lot. So is this conjugate gradient method? Okay. The trouble is if we put the word descent in here, first of all, it's wrong. Second of all, you're going to think that somehow there are descent directions involved. But this is a different view or a different approach to this optimization problem. Can the starting point x0 be any point in the conjugate gradient method? Answer is yes. Can be any point. It doesn't really matter. When can this method fail to converge? Any example, right? So, well, the method, as long as, so what is the prerequisite we had for this method? Did we have any requirement on A? Symmetric, positive, definite. As long as that's the case, this method is going to converge in how many steps? At most n steps. That's a guarantee, and there's a theoretical guarantee behind it. We've seen one proof that shows it to us in that way. How do we get the pKs for conjugacy? Right, in whatever we did so far, where did it go? Visualizing quadratic forms. Yes, I just introduced the idea of conjugacy. I never told you how we are going to get the pKs, and but I mentioned that the devil lies in the details and how we'll get it. I will talk about it in this class. Okay, given the matrix A, how can we tell whether conjugate vectors exist? So supposing I give you a matrix A, how can you be sure that any conjugate vectors will exist or not? It's positive definite, so it's full rank. Well, whether or not they exist again is something that we will see. Okay. Maybe we can have a look at this right away. Okay. Okay. So let's, as practice, let's say. So I'm going to give you A is symmetric, positive, definite. Yeah. Correct. I'm coming to that. There is one question exactly to count. Okay. So this is given to you. Do conjugate vectors exist? What is our intuitive feeling? Intuitive feeling is yes. It is sufficient for us to come up with one example when it happens. So what is the definition of conjugacy? P I transpose A Pj is equal to 0, I not equal to j. Okay. So how do we, I mean this definition is fine, but this definition, is it going to help me, or can it help me construct a set of conjugate vectors? So let's start with our road into this problem starts with the property of symmetric positive definite matrix. What is it for sure we can say about a symmetric positive definite matrix? It is invertible, something stronger. It is diagonalizable, or in other words, it has an eigenvector decomposition, right? That means I can write A as U lambda U transpose, right? What happens if I multiply on the right with U? U transpose U is identity because the eigenvectors, right? So the UIs are orthogonal. Okay. So we did this last time. AU is equal to U lambda, right? Now if I just take one, take this guy multiplied by one guy, what am I going to get? UI is equal to lambda UI. This is basically the what? Eigenvalue problem, right? Now what if I left multiply by UJ transpose? Right, so left multiply by UJ transpose, I'm going to get uj transpose A ui is equal to 0, I not equal to j. So what is that in plain English? What does that mean? The eigenvectors are a candidate for conjugate directions, right? They satisfy this property. That's all I need for conjugacy. So eigenvectors are conjugate directions. That means it exists. And will there be n of them? Yes, because there are n eigenvectors. Even if the eigenvalue is repeated, the eigenvectors are still distinct. This is a result from linear algebra. So I am going to have n eigenvectors. So there is no problem. I will give me a symmetric positive definite matrix. I can find you at least one set of conjugate directions. There is no guesswork involved here. Does this mean that this is the only candidate? No. I mean, I just took one example. This does not in any way tell you that you are limited only to eigenvectors. Okay. So this is how you get a system. I mean, this is one way of getting conjugate directions given the matrix A. Any doubts on this? Okay. Can you please explain once more how the step lengths, exact step lengths can be calculated for convex quadratic functions? So this was also a tutorial and also a quiz problem, right? So if I give you a, no, this is F rather, right? So who has trouble with this problem still? Should I, okay, let me put it the other way. Who would like me to derive this? How do we derive the exact step length given a quadratic cost function? Anyone? Oh, everyone is fine with it? Something, yes, no? Okay, who wants it? Raise your hands. Okay, waste of time. So everyone is familiar with it. In fact, the solutions were released and that also has it, right? It's, what is the calculus concept being used? Essentially, chain rule to calculate d by d alpha. That's what gives me the expression. And in the case of a quadratic function, if I had my f of x was like this, half of x transpose ax minus b transpose x, what was grad f? We could write it analytically, it was ax minus b, right? So when I substituted this into the expression for d by d alpha, I straight away get the exact step length, right? Okay. Yeah, so this was another student who said in the conjugate gradient descent method, as I mentioned, it is not gradient descent method. Why are the pk's valid descent directions, right? So this question really doesn't arise because we are not going at this problem from the point of view of descent. It will turn out that descent is also a quality and property of it, but that's not how we are looking at it. And how do we calculate the PIs? I give an example. Okay, Omkar asks, will performing Gram-Schmidt on the conjugate pKs give us any results which are advantageous? Okay. Well, once you get a set of conjugate directions, if I do Gram-Schmidt, the standard Gram-Schmidt on it, what will happen to them? They were already linearly independent, they will become orthogonal. Will they continue to be conjugate? Is it necessary? I mean, it's not obvious to me. Take a bunch of vectors, they are linearly independent and A conjugate. Now I do Gram-Schmidt to them. I don't see any reason why they will continue to be conjugate with respect to A. So that's not necessary. So it's not going to give us any advantage. However, he has inadvertently asked a good question. A modified Gram-Schmidt method is a second way by which you can arrive at a set of conjugate directions. Okay. So this will be one of the problems we will work out. Start with a set of linearly independent vectors. So You all know Gram-Schmidt, the recipe for Gram-Schmidt. Start with a set of linearly independent vectors, apply Gram-Schmidt, and that results into what? A set of orthogonal or orthonormal vectors. You modify that process a little bit. At the end of it, you get a set of vectors which are A conjugate rather than orthogonal. It's straightforward. We will work it out. Okay. So that is the second way of doing generating conjugate directions. But don't worry, we will discuss it. So this question seems to be by someone who knows a little bit more about optimization. Suppose instead of finding Ax equal to b, we want to add a regularization term as well. Can CG method be used for such a problem? Okay, so the question is that, let's take for simplicity. So we said, for when we started the conjugate direction method, we wrote our cost function like this, right? And we said that this is a better way than this approach, right? And the reason was, this second method had what? Had a condition number of kappa squared. This had a condition number of kappa squared. This had a condition number of kappa. So numerically, the first method is going to give us better results, and the second method will not give us as good a result because of the squared condition number. Now the question is, can I add a regularization term? So what this you will come across this word regularization very, very often. What does it mean? It means adding some term over here. Let us say, for example, something like this. Now what does this mean? We will study this towards the end of the course, but let's just get a sense of it because you will come across it in papers that you read and all. What is the meaning of this? Let's just intuitively understand this cost function. What is it saying? When will you be happy? In the real ideal world, when will you be happy? When the cost function goes to 0. That's the best case scenario. For the best case scenario to happen in this case, what should happen? Ax should be equal to b and x should be equal to x naught. That's the only possibility. Is that always going to happen? Most of the times it's not going to happen. Why? Because x naught need not be the solution to ax equal to b. Which means, if I go to the solution Ax equal to b, this first term is 0, second term has some non-zero magnitude, agreed? Come to the other side. Supposing I set x equal to x naught, second term is 0, first term need not be 0. So in both cases, there is some weight on either side. But now you say, I want you to optimize this. So the solution that you come across will neither satisfy this, the first term, nor the second term, but the value of phi x would be lesser than the first two cases. Now why would you be interested in such a weird solution? So this is a way of adding a constraint to the problem. You want to solve your original problem Ax equal to b, but you also want your solution to be close to some vector which you know. It has some nice properties. All those details are not important. You want the solution to be close to x naught, right? How close to x naught is controlled by this empirical parameter lambda, which is going to be problem dependent. So you can, at lambda equal to 0, you are driving the solution to x equal to b. At lambda tending to infinity, you are driving it to x equal to x naught, right? So this is a very, very powerful and common technique in image processing, machine learning, and so on. Add all the constraints to your problem in this way, right? This is simply here I've written the norm of x minus x naught. Another way could be, for example, what could it be? Okay, a common example in compressive sensing is something like this. Okay, so let's ignore this and write this. How do you interpret this? I want a solution to be as close to Ax equal to b, but what else do I want to minimize? The one norm of x. So one norm of x is something which, if you study signal processing, is something which tends to promote solutions which have very, very few non-zero entries. So there are image processing applications where this gets used, right? So there are lots of tricks you can play with this. Then the next question is, how do you get lambda? All of those things, right? So we'll study constraint optimization in the second half of this course. So this term which I've added over here is called a regularization term. So the question is, can the CG method be used for this problem as well? Okay. It depends on what is the regularization I add. This whole thing I can rewrite as a convex function. If I can write it as a convex function, then I can use my standard CG. If I cannot write it as a standard convex function, I can still use CG. I may have to go to a non-linear CG method, which we will study after we finish the linear CG. So the CG method is a very, very powerful method. Right now, it looks like we are using it to solve just AX equal to B, but soon you will see you can generalize it to a wide variety of problems. Okay, any questions on this? Has anyone heard this word regularization term? Right, you've seen it everywhere. So at least you have a basic idea what does it mean over here. Okay. Okay, question is how are we, so let me go to the, okay, the question is I wrote x star minus x naught is the linear sum, is a linear combination of the PIs. How are we writing this to start with? So, I mean the motivation is just coming from linear algebra. If I am in an n-dimensional space and I have n linearly independent vectors, can we say they form a basis? They form a basis. The meaning of forming a basis, I can express any vector as a linear combination of the basis. So the right hand side is simply a linear combination of the basis vectors, and that's any vector. Is x star minus x naught any vector? It is. So I just use simple linear algebra to say that the difference from initial to final point is some linear combination, and then I showed the nice part of this at the end of it was that the coefficients of linear combination ended up being exactly the step lengths that I chose in my method. So if I start with x naught and if I take these k values of alpha, I land up exactly where x star, the solution, right? Is this clear? Whoever asked this question? Yeah, the other question was about descent direction. So if you look at, if you look at the expression for alpha, let us just, for sake of argument, assume that my pk was not a descent direction. Okay, we are not interested in this descent direction analysis, but let's just take it for sake of argument. Supposing pk is not a descent direction, what will be the sign of rk transpose pk? It will be positive. If it is not a descent direction, it's going to be positive. Why? Because rk was what? Grad f, right? So for gradient descent, I needed to be in the quadrant of minus grad f, right? So if it is not a descent direction, it will be positive. That means what will be the sign of alpha? Sign of alpha will be negative, right? Assuming of course the denominator is positive. Okay. If that is the case, look at here, right? So I have xk plus alpha k pk. Alpha k is negative and pk is what it is. Now if I define a new vector qk is equal to minus pk, won't it look just the same? It will look like a step in the direction qk, which is now minus pk. Therefore, is it a descent direction? It is a descent direction. Is the step length positive? Step length is also positive. So we are back to square one. So we need not worry too much about descent direction over here in the conjugate gradient scheme of things. It's a different approach, and today's class I'll try to give you a geometric interpretation of how it is a different approach. Okay. What was the motivation behind this method? Okay, this when we do the graphical example, I will tell you what is the. So there was one question, I think, does linear independence imply conjugacy? So if a bunch of vectors are linearly independent, are they going to be conjugate? As we have discussed, there is no real compelling reason by which you can say immediately yes, they are going to be conjugate, right? It's not necessary. The question goes on, and all of these will be answered graphically. Okay.